Hi, good afternoon. This is the sixth talk of the technology afternoons at Petro-Explorers. Thank you for coming. Uh, the talk will be about the deep learning and its application in geosciences. Like basically, the focus will be on OpenDetect implementation of the deep learning plugin. So let's uh, start the talk. So what we, uh, as we went through all the five talks, all of them are available on Petro Explorer YouTube channel. Feel free to go in and check on previous talks. So today's talk will also be put in. That would be the next two talks, one about rock physics and pre-stack scenario modeling, and the simultaneous inversion workflow, which would be upcoming in next 2 weeks. We'll complete these series of the technical talks. Also, just to let you know, the OpenDetect YouTube channel also have a lot of related plugins and talks over there or webinars. So please take a look. So let's first introduce the what we do at Petro-Explorers. So we are a pre-stack, post-stack reservoir characterization company with seismic as well as wells and geology. So we are a GNG integrated reservoir characterization company, which starts the work with pre-stack gathers velocity and on the post-stack seismic inversions and various other attribute analysis. And we put it all together along with the extensive work in rock physics, petrophysics, and geology to put together to reduce the risk for the exploration and development, and to to predict the subsurface accumulations and various like hydrocarbon probability cube and various logs and facies and various analysis which can reduce the risk in exploration. The software base, we have been representing OpenDetect for last 12 years as a part of company. We're very focused on bringing in a lot of advanced new tools from OpenDetect. For quantitative analysis, we use Hampson-Russell. Along with OpenDetect plugins, we use Hampson-Russell for AVO and inversion. And then on the geological side, we are developing new software for QStrat, which does a lot of work for taking the log data and converting them into sequence stratigraphic models and cross sections and maps, which can then integrate with seismic to make a complete science model. Thanks Anastasia and team for that, and thanks Valentina for all the sequence stratigraphic work and supervision. Worldwide, we have extensive, many basins. We have extensive knowledge, especially from Western Canada Sedimentary Basin, going to Gulf of Mexico, many interior basins, and as south to Mexico and Colombia, and then to Argentina. So a lot of north-south, the basin extension, which is the most prolific basins in the world. And the series starting from Argentina all the way up to Western Canada. And then on the east side, we've been with the rift systems like Kenya, Tanzania, and Chad, when going into Nigeria, and on the India-Pakistan peninsula, where we focus on a lot of field development plans of small fields to how to develop them with the full integrated studies we've done in India about where the largest FTP provider within India. Today's talk mostly will be about machine learning solution as implemented by DGB Earth Sciences. So a little bit introduction of the DGB. It has a free base for everyone. That's the only full interpretation system which is free, and then moves to Pro. Pro have added functionalities to make it a full interpretation and visualization system. and then that brings in a lot of advanced plugins which are focused on various solving different solutions. So one of the solution will be machine learning. So let me introduce us to what is the machine learning. So machine learning is a bigger capsule part of the artificial intelligence, like artificial intelligence going back to 1940s and 50s as the computer started. That was basically computers were meant to process what human minds was processing by hand to cover it into. But artificial intelligence is where computers learn something and apply it on the other data sets. So that is what the basis of the behavior of artificial intelligence. So machine learning is a subset of it, which is usually covers the neural network analysis. These are enable machines to improve their with the experience. So the more data they see and the more improvement they can get. And further subdivision of this is called deep learning, which would be a subset of machine learning, which would allow a deep neural networks, which mean multiple layers of neural networks, to work to different aspects of the same problem and then combine the solution together. So that is what the basic of the deep learning, and it's been becoming one of the top analytical tools in the world. And as it is, we're going to go through how it is applied to the seismic data as well as log data characterization, how it can help us in our exploration and development. So supervised learning, machine learning could be supervised as classification or regression, which mean inversion, improving the inversion, or chimney analysis. And the unsupervised learning could be clustering through 2D or 3D maps or Conan SOM and various other methods, which we had in talk number 3. We went through all of that details. The machine learning plugin in OpenDetect contains, like, they put it together a control center. So that control center includes the previous work, which was neural networks, in one part of it. What is added is the seismic based 2D, 3D, some pre-trained models, as well as there are availability of both through the horizon-based or seismic bodies or seismic image segmentation. There are various workflows you can go through using the seismic, and the well data log-to-log prediction or lithology classification, like facies analysis and those on the logs, or it can also rock property prediction, which is seismic plus wells. You could predict the basically the inversion or improve the existing inversion using the log data and the previous workflows which we already used to. So machine learning, what it is good, finding complex relationships between structure and the data set. So usually it's a scaling issue, like the various scales of data, it is difficult to put them all together. Like, it's like how human perceive, like, the height, color, face expression. So all those things we put together, or walking style and various, in order to recognize a person. Is the same way as that in the subsurface geological model, you are seeing pieces of this information. Like your seismic data have a different scale of investigation with its errors. Well logs have a different scale at higher frequency. The observations, like descriptive observation, that Hamaki signature or this various observation, have a different scale. Outcrop and microscopic levels of petrography, and those have different scales. So the idea is to learn from each scale and combine them together into a complex learning environment, which would make it computer to recognize or classify certain areas. So in general application, we have seen a lot of them, and we are bombarded with the advertisements based on those results of the computer analysis of what our driving what our habits and other things are. So a lot of things are developed for computer vision, playing chess, playing even many other games now, and driving cars, robotics, and as it goes on and on, and like there are a lot of things which are implied in the it's not new in geoscience. Actually, geoscience had an older and much mature audience, because we have been using these neural networks for a while now, since late 90s. It's been extensively used in our inversion, in our petrophysics, which is like fuzzy logic, and those for lithological classification. So a lot of things are base neural network for use. But since 2012, when talking about the deep neural networks, because of the computer power and things coming up, now we have a lot more new applications as advanced from the previous applications. So let's look at, this is one, like it's a very wide area of machine learning. Like there are new methods popping up every day, like you might have heard about random forest, XGBoost, ADA boost, various gradient analysis, for so some statistical basis. So there are various bases of doing the analysis, and then there are supervised and unsupervised learning methods and neural network and deep learning. So initially, when we talked about in the last talk or the before about neural networks, OpenDetect implemented what called the neural network perceptrons. That perceptrons were already a deep learning layers, like it was already more than one layer, but it was the vector quantization or multi-layer perceptrons. So it was already a multi-layer scenario implemented before. And in unsupervised learning, we had clustering, k-mean methods, and those implemented in order to do Bayes analysis. So this was the basis, and I just gonna review what it was before in next few slides, and then go toward the deep learning. So what we talked about, the chimney analysis, like you pick the areas where you have, think it's a vertical migration path affected the seismic. It picked up that area and the areas which are not chimney. So you pick the two spots, chimney or non-chimney, and then you have calculate various attributes to find out how we can differentiate between those two classes. And that is called the supervised learning. So it would create a output, which would be to yes or no. So which is actually not only yes or no, it would be a probability of yes and probability of no, which mean probability of yes, like saying that it's possible chimney vertical migration. It's through some of the faults. These are the where initially it was called gas chimney, but later it figured out that under the pressure, equally, the gas and any other hydrocarbon molecules, when they move, they affect the seismic. So this is actually called the hydrocarbon chimney expulsion, how the hydrocarbons migrate through the earth. And that is one of the big method was introduced by Statoil, now called Equinor, and then implemented by DGB and worked by DGB as the main analysis. And they have a complete atlas now, the chimney cube studies. All the worldwide chimney cube studies are put as a atlas. You can become a member of these atlas, where you can see all the examples where DGB and others have worked on, and they introduced their chimney examples to be available. The worldwide, there are more than 50 examples in different basins of the world, and you can see and you can relate it to the production. So what we saw, that cause of dry holes is majority of the causes related to charge and seal. Uh, uh, so seal is the what chimney would reduce. Seal problem of the CO or the covering beds, as well as the charge, like is it migrating into the trapping system. So those two were very good in risk analysis and reduce the uh, reduce the failure problem with the why something is failed, why there are very small accumulations, because the migration might not have happened. So those studies were like really important. And there was 100 from North Sea, 100 traps were analyzed against the chimneys, and found that which kind of traps are how the chimney should look like in order to like a cloudways or side leaking through the spill point leaking, or if it is leaking from the front, that would be a leak trap, and that would be uh, it's better to avoid drilling certain parts. So it's reduced a lot of risk. So there were 50% success rate when it was chimney was selling leaking. So now I come to the deep learning. From the machine learning or original neural networks, which were implemented back in late 90s, going into the deep neural network, which is now. So one of uh, uh, OpenDetect have been one of the pioneer software to bring it as a plugin and implement all these deep learning for geoscience, getting that is the fastest to the market, coming from all of the knowledge we are getting from the deep learning research. So new machine learning plugin would cover supervised learning in a classification, in a logistic regression, linear regression, polynomial, into the regression work. The same older work is still part of it. Then ensemble learning using bagging and boosting, random forest and XGBoost, which is the gradient boost and the random forest. We'll show you some of the examples. And then in the deep learning neural network, I added the convolutional neural network, its various implementation, and uh, autoencoder, as well as perceptron in the same way. Yes, there are many other, now it's open to learning. Many other methods can be automatically run through uh, connection through the Python or others connecting to the Amazon and other servers or other neural deep learning methods. So there is a lot more application in this recent deep learning release. The basic difference between simple neural network and deep neural network is the layers. The number of layers which would depends on how many layers to perceive in order to get the weights between the input layer and the output layer. So the classification can be more than yes or no, or a simple yes or no. It can be multiple facies in those, and we'll show you the example of that. Now, the first major, again, looking at the fault problem, which we OpenDetect have been solving through its fault and fracture plugin and through the multi-attribute fault detection and extraction. Now, there is a new machine learning way of further enhancing. It's called the UNet, and it's already pre-trained based on the synthetic data set as well as the fault data set to used as a training data set. So all these training data sets, so when you get to machine learning plugin, it is also part of the machine learning plugin is the predefined or pre-simulated trained data. And it's simulated based on the many small cubes, 128 by 128 cubes, where the result is known because the result is generated from a synthetic cube with faults inside. So that means our machine learning is how it is image would look like when the faults are inside. So synthetic images and then some real data is part of the training. So what we see as a result, like when you run this pre-trained neural network, you get right away pick up most of the faults. Of course, you need to, there is some preconditioning involved with the seismic data in order to enhance the faults. And that's what I'm going to show you the image processing as an input. So there are certain tools as a part of the Open Detect arsenal is the getting first from the original data, a run called dip steer median filter using the structural steering plugin called dip steering plugin to improve the linear continuity while enhancing the fault attribute. Then we called edge preserving smoothing. So what it does, the edge preserving smoothing will preserve all the edges, so all the faults are preserved while the rest of the data is extremely smooth uh, in between the faults. So that is goes as an input of the machine learning so that it would not have too many errors. So comparing to from input data to these, it preserves its location of the faults while smoothing rest of the data. You can see down here very clearly there. Otherwise, it would be hard to decipher these faults would be coming then in this. So as you go through the unit, predicted faults could be then defined well defined, and they have all these three directions, which mean dip, strike, and the dip throw, as well as it can be found out the throw afterwards. So the unit predicted faults, uh, and this is like just sliding through the raw seismic, and then in this part you see the filtered seismic. So very rough, the amplitude balanced and filtered with the AGC and edge preserved smoothing filter. And when you run the unit, you get a single sample fault system, which is means you can go without this pre-processing steps and end up, and it's all in the very guided by these. Of course, you can always create your own UNet system. So UNet is actually uh, kind of a convolutional network with 3x image input data and output segments. So it is segmenting the output to a uh, narrow narrow output. It's because it's shaped like U. It's a multi layers, and you come down to these layers so that it's classified. So it splits the image and then classified. So image processing technique. Um, so predict missing. Now the other application of UNet would be the filling in the gaps in the data. So that is for 5D interpolation, and those algorithms, it haven't yet been applied to all the 5D interpolation algorithms and those, but we're going to show you example of the post-stack the interpolation. So looking at how we prepared this, that we took a 3D and then we created called the 33% or 1/3 of the traces randomly. We took the random traces out. There is a very nice presentation by Paul de Groot about the process, how to do this. But you can create the data set with the random, and then what we are looking for how those traces can be filled in. So naturally, the training data, like north part of this is a training set, and then south part is used as a blind test zone. So when we go through this, we select for a unit to do so, taking the blind test area. So we created these 33% blanked out traces. So which means if you're missing like 1/3 of the traces, it applies quite well to the megabin and those, and it doesn't really matter where you train it. You don't have to train right on your data set. You have a multiple training from another data set, and then or to to see how it would interpolate, because it learns again the dips and strikes and everything from the training. So once you have the blank one, and then UNet then filled it. So if you look at now against the original versus UNet, it's hardly you can see any difference. between these. But the same another example of these in this case, we have inline from in this case the data was trained from a Delft data set and applied to an offshore data set of the F3. So from a Delft data set, create the training, and then blank out the F3 data set with the 33% random blanking. And then when you apply that neural network, which is trained over Delft, is the what you see is a difference. And now you can see the difference, especially within the some of the Hamaki, this mass transport complex area. You can see there are some differences, but most of the way, so it means 1/3 of the data set, you could be small gaps which are missing can be blanked out and then interpolated using this network machine learning in order to get a full picture good for interpretation rather than having a noisy traces in between. And then you can take that concept into the pre-stack level and use it for 5D interpolation or binning or increase the binning, and various applications can in a pre-stack and post-stack domain. Now move to the another application, which is called the facies method. Now you saw the method of the chimney analysis that can be extended in deep learning as well. In the deep learning, you can have various chimney or non-chimney chimney areas, and then you can classify. Or we can now OpenDetect also have a brush functionality, so that you can make certain areas as brushing, that these are my clinoforms, and these are my channel systems, and these are my salt dome. So all those things can be put in as a supervised as a point set can be given, and then we go into the machine learning classification or deep convolutional neural network application of one of the convolutional network to come up with the results. It can be defined through the model. The lab results again, I mean, these are the multi perceptrons, and these are like multi-layer perceptrons, which were the previous neural network showing the chimney. Now these are new defined by the convolutional neural network as the same data set to showing. So there are a few applications, of course, pluses and minuses depending on how much data is used for training and how much data you can take the multi-layer perceptron, the shallow neural network, and then train the data with that into the CNN, and that come up with a very defined facies or the probabilities. So the other application is the seismic facies classification in a 3D domain. Like it's a very good example on a YouTube with Paul de Groot explained the channels, separating different type of channels from the sandy channels to the facies to the various attributes within the channel system. What you see is just go back. What you see is normally amplitude analysis versus a facies to pinpoint the channel system to separate it out as a facies. So there are eight different seismic facies with the results being 1 to 8. Being the results of the unconfined channels, floodplains, and various can be all separated, and then put it against the wells. This is again modeled through the Thalweg tracker, which is another comes with OpenDetect Pro, is the Thalweg tracker. So you can actually pick the channels only and not spill over into the rest of the data, and then you follow, and you can use the convolutional neural network called LeNet to classify those into the channel system. Now, last example I want to define is that we explained it before the many times, the hit cube inversion, which is a pseudo well generation using synthetic properties and then simulating those properties. In this case, we've defined the property ranges and defined this random forest uh, uh, so we're trying to use the random forest to predict the VPVS ratio, porosity, impedance from pre-stack data. So in this case, we created a pseudo wells, simulated pseudo wells from the Synthrox stochastic simulator to create 20,000 pseudo wells. Now using those pseudo wells, and using the random forest machine learning method, we end up now the results. First is the hit cube method, which is again one by one trying to find the best match, and the other is the random forest method, which is automatically going to find its own attributes to match. So that once you apply those, that is the differences what we see. Some have preference of one or the other, but the hit cube method, this is the inversion slice over the acoustic impedance over the whole 3D. And this is using the 5 angle stacks and using random forest, deep learning, in order to get these results. And you can see a lot more details in there. Like, sometimes you don't want that details and that precision, but it is coming up with those system and various attributes what it's picking up from the seismic or all the 5 angle stacks. And this is the normal like not normal but the hit cube inversion of probabilistic method to come up with the average map. So there is another method which mean it could be applied to all inversions of various going directly from the attribute into a pseudo-well method. So you still have to go through pseudo-well method, but you can use machine learning to invert these ideas. The yeah, but that was not last. That was the last seismic example. But once you come to the well prediction, it's extremely powerful well prediction algorithm to come up with the well prediction based on you train where you have all the well logs, and then you have the target log as well. So if you have like 10 wells with the target log, like say porosity, and you have all the rest of the logs, and then you train your data set based on that the logs. Input logs could be sonic and density or resistivity, gamma ray resistivity, density, and sonic to come up with the porosity. But that is if you have an existing porosity for few wells, you can train your data, your algorithm, then it will predict the porosity for all the rest of the wells. So this is again this showing the example which was not in the original. This log is not part of the training data set, but it did come up with a very close relationship. Of course, density and porosity have a very good relationship already, but I did try on some of the others is to predict density from sonic and gamma ray, which is like using only 4 wells to train. And what you see is on the top, the green, uh, the well, it's turquoise, but it is the green overlay is the predicted log based on the sonic, and green is sonic, and the yellow is gamma ray. And the original density is on the behind. And so you can actually use it. It is called the method called the extreme gradient boosting, which is the XG boost, one of the prediction algorithm from the uh, deep learning. So there is a lot of potential in all of the areas of the deep learning. which you can use it for training, like the map-based or volume-based neural networks with fault interpretation, and those going into seismic applications of like a facies mapping of the whole 3D facies mapping, or the chimneys and bees analysis, which is supervised learning of various classifications, to log prediction at the pre-processing when you have missing logs, like shear log prediction and various. We already use formulation, but we can use deep learning to learn that. Or seismic to well application is coming from inversions, or as an input inversion or input as a pre-stack stacks, like angle stacks, and coming up with the predicted inverted rock properties volumes. So you can predict any of those. So there is a lot of course, there are a lot of tools involved in pre-processing of the data. And again, DGP or OpenDetect provides all that base tools of each of the sequence of the things to in order to process the data for each of the functions. And a lot of rock physics and filling in gaps and areas you can define in the log processing application, as well as many tools to pick the your input area. So that is the so that's acceleration. So DGP offers a lot of broad range of plugins, and of course free base interpretation system. Plus, many times you can open up various plugins and work advanced things and go back to the base system to work through. So DGP has been always on the front end of new tools and new methods to implement in the um, for the seismic and for the well logs analysis and sequence stratigraphy and various. They've been pioneer of many things and many advances. Then now they brought in the machine learning plugins, and as many of us now think as that we becoming obsolete as a humankind, or as a so in a post-human world there will be ever advancing solutions ready to be created to function and with or without us. So so for now we are making those happen through our user input a lot of time, but you never know in the future the user input getting less and less. And Petro-Explorers, as usual, we represent OpenDetect in Canada, and we provide services using all kind of tools, not only limited to OpenDetect, or we use Hampson Russell, we use GS, we use various other modeling software, Petrel and Sizeware, and various other interpretation to combine the best solution for the company. So, and we are always ready to help in any way in the process of the OpenDetect, the use of OpenDetect, or anyone want to give it a run for the deep learning. So that and thank you for attending, and we look forward to um, helping evaluate the deep learning as well as the services. Thank you. Any question?